So, all right, start recording. So for the ones that entered a little bit later, good morning. So today we have the third day of this mini course on Tomita Takesaki. So the plan for today, I've had set a plan which I hope to be able to cover in 2 hours. It's always surprising how short 2 hours can be. Uh, so my idea is, okay, I will start with basically paying my debts of showing the details I forgot yesterday, and then we are going to follow the plan I proposed it in the very beginning. So talking about some properties of the modular operator, talking about the Tomita Takesaki theorem, KMS states, and some physical kind of ideas in which modular theory show up. Okay, so without further delays, let me share my screen. Yeah, okay. So I was like, the last thing I advertised is basically, again, what I said from the very beginning, that you have this kind of like strange behavior in physics. First, like the vacuum being cyclic and separating is already kind of surprise, which is a consequence of physically reasonable assumptions, showing that, okay, physics is not so well behaved mathematically. Yeah, so that's the pathological example. It's not a mathematical pathological example, but this pathological example is physics. And then we see these Tomita operators, which are most of the time unbounded operators, uh, and they are kind of all defined in dense domains. They coincide in the common domains, but they cannot be the same. Yeah, so since they are closed already, it's not possible that the closure of the Tomita operator for a smaller standard subspace coincides with the one for the bigger. So they are really different. So the even though the domains are always dense, the kind of discontinuity that those operators have basically do not allow you to extend it further than the domain where it's already defined, in particular because it's already closed. Yeah, so okay, you can extend it, but not only with the information you have in the operator. Yeah, so if you have SH1, you don't get any information about H2. Okay, so let's try to understand a little bit better these operators, because we at least learned some things about those operators. So if you have H, a standard subspace, we learned that we can construct some operator, SH, which has the following properties. SH is closed. Yeah, it's a closed operator. Also quite interesting, so it's antilinear. So SH is antilinear. So just with the easy stuff, antilinear. It's an involution. Yeah, so remember that SH will take a vector of the form H1 plus I H2 and gives us H1 minus I H2, which means that SH is almost the identity. So here I will be very precise. Most of the time we will just write, oh, SH is the identity, but it's not true precisely. So it's identity restricted to the dense subspace, which is again a little surprising. Yeah, so you have unbounded operator such that the square is the identity, and therefore uh, the square can be continuously extended precisely to the identity. Yeah, so that's a continuous operator, which is again first time you see may be quite surprising for the ones that got used to that. Like when I look and say, yeah, sure, that's natural. But first time I saw it, it was definitely not so obvious what was going on. And my claim here is that the reverse is also true. Yeah, so that's if you have an operator which is a closed antilinear involution. Yeah, and by involution it means exactly that SH square is a restriction of the identity. then you can reconstruct your standard subspace H. And how do you do that? You just set H is equal to the fixed points of SH. Yeah, or you can also say it's the kernel of SH minus identity. Yeah, so that's well, for obvious reasons. So the fixed points means that SH, it has to be in the domain, so it has to be of the form H1 plus IH2, and that gives you H1 minus IH2. But if it's a fixed point, it's also equals to H1 plus IH2, and then well, the H1s cancel out, but then it implies that the H2 is equal to 0, which means that from the beginning, the vector H1 plus IH2 was just H1, which lives into the standard subspace. So one can check that if you have a closed antilinear involution, this H that you obtain by this formula is a closed real linear subspace, or it's a subspace, a standard subspace. Yes, just for short, is a standard subspace. Okay, so there is a one-to-one correspondence between Tomita operators. Yeah, so closed, maybe one thing more, closed, densely defined, densely defined operator. Yeah, so there is a one-to-one correspondence between closed, densely defined antilinear involutions and standard subspaces. So if I have one, I can construct the way I described it before. And if I have say the candidate to the Tomita operator, I just define the standard subspace as being the fixed points. Yeah, so there is this one-to-one correspondence between the two things. Okay, but from the very first day, I warned you that closed operators would be important. Okay, so they already showed up quite a bit up to now. But also we talk about the polar decomposition. So notice that SH is almost in the precise requirements for talking about polar decomposition. So the only missing or the only mismatch is that SH is not a linear closed operator, it's an antilinear closed operator. Okay, so what do you do? Well, basically this almost the same theorem follows. So just for giving you an example, define this operator U that goes from the Hilbert space into the Hilbert space, and that takes one basis, so it's a basis-dependent operator, but doesn't matter which one, so just take one orthonormal basis, and you take the vector which has the coefficients alpha n, en, and en is my orthonormal basis, and you associate the vector alpha n bar en. Yeah, so this is an antilinear, in fact, an anti-unitary operator. Yeah, so it keeps norm. It's a bijective. Yeah, so this is again an antilinear operator. So I can just look to U times SH. So U times SH is now a linear closed operator. Yeah, since U is bounded, the product of U by SH is closed again. So we have now a closed real linear operator. So this operator admits a polar decomposition that we'll call, I'm not sure how it should call, let's say V times, and I will call it delta H 1/2. I will define delta H in a second. So you know, okay, where V is a partial isometry. And SH, oh, sorry, and delta H is equal to, so it's the star of this operator, so that would be SH star U star U SH, which is just SH star SH, because U star since it's anti-unitary, it's just the identity. Okay, so the delta is just the same formula for the polar decomposition. The only thing that changed is V. And then it implies that SH is nothing but U star V delta 1/2 H. And this thing here I will call JH. Yeah, so it depends on, I have omitted the dependence on the standard subspace, but then what I'm saying is that this is just delta H 1/2. Okay, so I just was like use this trick. That's a common trick that you use when you have antilinear operators. You just get one antilinear operator that you can construct using an orthonormal basis to say basically the results I already had um, for linear operators have kind of an analog for antilinear ones. Yeah, so here you see I have again a polar decomposition of SH in the form a partial isometry. The only difference is that it's an antilinear partial isometry. And here use just the modulus. Yeah, so that's just the same thing as the modulus of SH, which is the square root of SH star SH as before. Yeah, so this one doesn't change. Again, because the product of two antilinear operators is again linear, so SH times SH star is just back a linear operator, so the square root is just the square root of the positive linear operator given by that formula. So no news into that direction. Okay, now I have opened up like well, in some sense Pandora's box, but also marvelous new ideas, or like just out of this information I can learn a lot about modular theory. So here what we see is these two operators, which are oftentimes referred as the modular data. So JH is called the modular conjugation. And delta H 1/2 is the modular, or delta H, in fact. Yeah, so delta H is the modular operator. Okay, what can I say about JH? So first things first, what is the kernel of SH? Answer is just the null vector. Yeah, so SH is injective in its domain. Yeah, it's of course not defining the whole space, but the only vector that gives you 0 is the null vector, meaning therefore that JH has to be bijective. So it's not only an antilinear partial isometry, it's an antilinear unitary. And so SH is injective and has dense range. That implies that JH is anti-unitary, meaning that JH star JH, which should be the projection. So you have two options. So it's JH star JH is the initial projection, so the projection into the orthogonal of the kernel. So that's one, because, well, the projection into the orthogonal of the kernel is 0 because the range is dense, but also JH star, which is the projection into the, well, basically the same space, but for the star is also dense. Yeah, so kernel, so there is no, so the kernel should be the 0 projection. So here it's the projection into the orthogonal of that, and the other one is the projection into the to the range. Yeah? So that's one is for the operator S and the other is for S star. Okay, so we have an anti-unitary J. What else? So I can also check what is SH and compares it with SH inverse. Yeah, because I just realized that if you apply twice SH, you get identity restricted to the domain of SH. So these two operators are the same. Yeah, so they're defined in the same domain and do exactly the same thing. But from one hand, the left-hand side, oops, the left-hand side is by definition JH. Well, the definition of bipolar decomposition, we just use it. The modular conjugation times the modular operator, the square root of the modular operator. And I can also decompose the right-hand side just, well, saying that the inverse of the product is the product of the inverses in the opposite order. Yeah? And this, the inverse is just JH star. Okay, but then I also can write it into a, in some sense, strange, but also a nice way, let's say. So I can write that as JH star, JH delta minus 1/2 H JH star. So I only use the fact that this is the identity. Okay, but look now to these two operators. So I take my S and I decompose it as a partial isometry and a positive operator. And here I have a partial isometry and a positive operator. Well, then I know exactly what these two operators have to be, and they have to be the same because the polar decomposition is unique up to the points with the kernels, which do not exist. Yeah, so here we don't have kernels. So what should happen is that JH should be equals to JH star. Yeah, so the partial isometry has to be the same. And the modulus of the operator has also to be the same. Okay, so here, I'm not sure if it's obvious to everybody. So one thing that you can do is just take the definition of the modulus, right? So you just take this guy star times itself, that gives you delta. And here the same thing with this one. So remember that J times J star will give you identity, which means that we'll have just the product of this with a star and itself, and the J's in the middle cancel. So you are going to get J's around, or maybe easy if I should say it this way. Oops. Yes, -1. Yeah, so it's just multiplying the star of this thing here times the operator itself. Yeah, so it's the J's in the middle cancel, and you get 2 times the delta minus 1/2 in the middle. So it's just so basically I'm using the uniqueness of the polar decomposition, but it's also an immediate calculation. Yeah, so that's if you just take the S star times S with this formula, what you get is yeah, so that would, or maybe I should just do it. JH delta H minus 1/2 JH star. So that's the left-hand side. And then you have to put the right-hand side. So this is the star star. Yes. Yeah, so it's the star of the one in the middle times the JH star on the right. And now you multiply by SH. And then the same thing. Oops. JH star. Yeah, so this is equal to that. These two operators cancel out. These two operators cancel out. So I get JH delta minus 1/2 with delta minus 1/2 is just delta minus 1 and JH star. Yeah, so just as I claim here. Okay, so it's a simple calculation after you realize that the JH has to be anti-unitary. Okay, so in fact, I get like some of the most important relations for modular theory, because that's using the first formula that also tells us that delta H is equal to JH delta H minus 1 JH. Yeah, so conjugating the delta with J's give you 1 over delta. So even more general, if you have a function of delta, so if you have f of delta h with jh, that gives you f of delta h minus 1. Okay, so that's even more general formula holds. This is just a little trick playing with spectral projections and realizing that from this formula, it means that delta IT and J commute. Yeah, so that's maybe another way of saying almost the same thing with delta H IT that is equal to 0. Yeah, and that here you have to be careful because remember that when you conjugate J with delta, you get a delta. Yeah, so J with delta IT. On one hand, you can pass the, or maybe just the J on the other side. So you can pass the J to the other side to get a delta minus 1 IT. But remember that J is anti-linear, so you also get a minus with the I. So the two i's cancel out. Okay? So the fact that J is anti-linear plays a big role into this relation. Okay? Okay. So that's what we call the modular data. But why modular data is so important? Just let's check if I'm going in the correct order. Yes. Yeah. Why is it like interesting and relevant? Well, for several reasons, but let me start with, in some sense, I will call, well, let me tell first what's the result. Tomita, Takesaki theorem for standard subspaces. And the claim is the following. If you have, so I'm not going to write too much, so I'm just going to like keep the most important ideas. So if you have a standard subspace and you have your delta IT, yeah, so how I'm constructing this operator? Functional calculus, right? So you have delta is a positive operator. Therefore, functional calculus allow me to define which is delta to the power IT. Yeah, so that's remember that the function lambda to IT is well defined as far as lambda is a positive number. Otherwise, I would have some issues with analyticity. Okay, I don't know what to say, what's a power. Yeah, what's minus 1 to the power pi. Yeah, so I cannot continuously extend it. Okay, so what does this operator that I defined through functional calculus do? Well, it keeps the standard subspace invariant. And if you have your J into H, it gives you another space, which is called H prime, or I call it H prime. And what is H prime? Is the set of all vectors, which I will call again H prime, in the Hilbert space, such that the imaginary part of the inner product between H and H prime is equal to 0 for all H into H. Yeah, so it has to do with the imaginary part of the inner product. And here you again start seeing how the complex structure of the whole thing is quite important. Yeah, so we start to look into a real subspace. Out of this real subspace, we construct a complex one, namely this one. For this one, we can look to this Tomita operator, which is this densely defined. I can acting as a modular, as a complex conjugation. I can look to the polar decomposition of the conjugation. And in the end, we see it has to do with the imaginary part, like of the inner product. Okay? So let's see how it goes. So in this case, the proof is quite easy. So first, let's see what is SH calculated into ITH of H, where this small h belongs to the standard subspace H. Well, this is SH delta 1/2 H delta IT H, but then this delta IT commutes with this delta H1/2 and also commutes with J. Yeah, so the only the delta IT, the delta 1/2 not, but the delta IT does. So then it's just, I can pass everything to the right. So it's SH delta 1/2 H in H, which is nothing but delta ITH of SH into H. But since H is in the standard subspace, we know it's fixed. So it's delta ITH of H, and that's for all H in H. Well, but then it implies that delta ITH of H belongs to the fixed points of SH, which is precisely the standard subspace. Yeah, so it keeps the standard subspace invariant. If you use the same relation saying that SH is SH minus 1, you see that therefore the two spaces are the same. Yeah, so that's from here I just conclude that ITH into H is contained in H. But then I can see, well, for all T, but then I can do the same thing with delta minus IT H into delta IT H of H, which is H, and that should be contained into delta minus IT H of H. Yeah? So I just applied delta minus, so I get this result saying that the left-hand side is contained to the right, and I apply delta minus IT on both sides, and of course the inclusion is preserved, but then the deltas on the left-hand side cancel out, so it's just give H, and that should be contained in the other side for, again, for all T in the real numbers, so in particular for the negative side, yeah, so the negative sign, meaning the two spaces are the same. And the second one is the one with J. And for that, I first notice what happens if you take J, H. And again, I use the fact that H is invariant. So this is H, J, H, S, H into H. And using the polar decomposition, it's JH, JH, delta 1/2 of H in H. But then the two J's, remember, JH is equal to JH star, and JH times the JH star is 1. So this thing here is just identity. And delta 1/2 is a positive number, so this thing here is positive. Okay, so that's not the final conclusion, but true. Yeah, so if you take, which is also surprising somehow. Yeah, so if you take elements of the standard subspace and you calculate like the sandwich with of JH with these vectors from the standard subspace, you always get a positive value, even though JH is not a positive operator somehow because it's antilinear, so it's a strange thing, but okay, but it behaves in the vectors of this form as if it was a delta 1/2, which is a positive linear operator. Okay, but that's just a small comment to tell you that this curiosity that does not extend to the complex span. Yeah, so that's maybe that's the whole point. Okay, but then what I want is to really look what happens to JH with any two vectors. Yeah, so the inner product between a vector in H and another vector, not necessarily the same. And for that, I will use a small trick. Namely, I will separate this into H1, JH, H2, and then the other half of the same thing. Oops, H2. Okay, and now I use my Blackboard powers to erase the second one. I've just write it into, or maybe I can just keep going with the calculation. Okay. So, okay, first term is the same. And for the second term, I will pass the JH to the other side. Okay, so I have a question. So it's because the probability needs to be positive. Yeah, so the positivity is because the operator delta H was defined as a positive operator. Yeah, so it was, so delta H by definition was SH star SH, and operators of that sort are always positive because if you calculate X delta H X, that will just be X SH star SH X. And then, of course, this is just SH. Oh, this star disappear because I pass it to the other side. X SH X. Even though it's unbounded, of course, I have to calculate into X, which is in the domain of the operator delta. Yeah, so that's a requirement. And that's just the modulus of SHX square, which is always positive. So this delta 1/2 is, the full delta is a positive operator, and the delta 1/2 is just the square root of that one operator. And the square root is again positive, yeah, because it's defined through functional calculus, and therefore the spectrum would be just the spectrum of the given operator, meaning it will also be a positive one. Yeah, so that's some requirements. So in particular, if you ask what is X delta 1/2 HX, that will be just the norm of delta H 1/4 in X squared. Now, so just because you can break the delta 1/2 into delta 1/4 times delta 1/4 and pass it to the other side. So it comes from the definition. And of course, because the two vectors that you are calculating, on the left and on the right, they are the same vector. Yeah. Okay. So I hope now that's clear. So let me go back to my small trick. So what I am doing now is just passing this J to the other side with a star. But remember that J star is equal to J, so I have no stars of J. But also you have to be very careful because J is antilinear. And the adjoint of an antilinear operator not only pass to the other side as Sj star, H1, H2, but I have to be careful because I get a complex conjugate. Yeah, so that's the definition of the adjoint for antilinear operators. You not only switch the side, but you also conjugate the inner product. Otherwise, things go very strange. So here we have H2, JH, H1. Yeah, so just flip the inner product. That's a property of the inner product. Okay, but then I can write this into an interesting way, or that's at least convenient. I can write that as H1 plus IH2 and then the JH with H1 plus IH2. And as you can all easily see, you have the cross terms, that's the ones that's showing up above. Yeah, so that you have the H1 with J with IH2, but you also have, oh, sorry, no I's. I am too often using the I's. Yeah, so you have the H1 with the JH2, which is this term. You have the H2 with JH1, which is this term. But you also have the, let's say, diagonal terms, which I have to compensate. So I have to remove H1, JH, H1, or which I have to remove just for the equality to be correct. H2, JH, H2. And now the equality is correct. But as you see, the first term is real, even positive, because of what I mentioned before. Yeah, so if you take the same vector, you get something positive. This is also positive, and this is also positive. So the result is not necessarily positive, but it's for sure real. Yeah, so it's a subtraction of uh, positive numbers. Yeah. Okay, then what I realize is this thing here. So hence, H1 with JH in H2 belongs to the real for all H1 and H2 in H. Well, but if it's always real, that means that the imaginary part is zero, which is exactly the definition of JH2 belongs to H prime for all H2 into H. Okay, so what I concluded is this thing here is contained in H prime, but if you apply H prime again, so JH of JH, H is contained in JH of H prime, but then you immediately see what is the prime of the prime. Yeah, so this is the JH of the prime. And this is just H is also contained in, sorry, here is, yeah, so H is also contained in. So I did something wrong. So it's JH is contained in H prime. So I applied J on both sides. So H is contained in JH of H prime. Oh, okay, so here I get something strange. So that's not what I want. What I want is maybe the reverse inequality, which I will require some other detail to do, but okay, fine. So I can do the same thing. So for now, okay. The question I wanted to say is like, what is JH of H prime? And my claim that this should be then contained in H of prime prime. So I'm and applying again. Yeah, so I'm just taking the JH of H prime should be contained in H prime prime, which is just H. Yeah, so that's just to say that they are the same. It's equal to this one. Oops, this one. And here you should complain, and that's why, okay, I forgot that I should have mentioned that before. So here I'm using that JH is also the modular conjugation for H prime. Yeah, so I'm basically applying the results that I just proved for H, for another standard subspace, which is in fact another standard subspace, which is H prime. And the reason for that is I can ask what is the SH star. So nobody asked that up to now, but maybe you have wondered in silence when I was talking about this SH and SH star. We know what's SH, but what should be SH star? Well, for sure, it should be delta 1/2 H JH star, just because of the polar decomposition. But then if you pass the J to the left-hand side, as we learned that the relation should be just delta H delta minus 1/2 of H. And this is another Tomita operator, so it's another antilinear involution, yeah, closed antilinear involution, just because of the relations we had before, yeah, so that's densely defined because the operator SH is closed. Since SH is the identity restricted to H plus IH, you take the stars to imply that SH star is also a restriction of the identity. Not clear what's the domain, but it will be because of the taking stars on both sides. So it should be true that this SH star is the Tomita operator for another standard subspace, and this standard subspace is exactly SH prime. Yeah, so that I will give you as an exercise so you can check that it is in fact the same Tomita operator. So it do the same thing into this other space, so it's the correct characterization. And from that, you see that the modular conjugation of the Tomita operator for this so this operator is called, this space is called the symplectic complement. Symplectic complement. So the modular conjugation for the symplectic complement is precisely the same as for the space H. So why we need the standard subspace to be real? Yeah, so I will mention a little bit like these real structures into a second, but there is at least one initial reason why one can claim it is more physical than the whole space, and the reason is the same reason that the algebra is less physical than the observables. Yeah, so the observables have to be with self-adjoint operators, which is just a subset of your algebra, and this is just a linear subspace, real linear subspace. Yeah, it's not even an algebra. Yeah, if you multiply two self-adjoint operators that do not commute, what you get from the star is not the same. Yeah, so it's not even an algebra. But so the self-adjoint operators are just a real linear subspace. So a real linear structure is relevant because the physical information we have comes from the self-adjoint operators. Yeah, so it's one could easily ask, what does it mean to have like some position operators plus I momentum? Well, it's not really a very physical observable because it's not an observable. Yeah, so that's so what's the star of that? So it's x star minus IP, which is okay, another operator, but not something that I can get physical information. So I can really not measure anything from this operator. So this has less physical reality than if you take a self-adjoint operator. And so what I'm saying is the difference between, okay, so the Hilbert space seems to be related to taking all the operations could be local or non-local. That's not the important thing, but it comes from the algebra applied to the vector and take the closure, while the standard subspace is only the information that you can get throughout self-adjoint operators. So basically, one is what you can get for whatever operator you acts on the vacuum. It's the second one is what you get only for observables, or at least potential candidates to observables into the vacuum. So the real structure is relevant for physical reasons. Yeah? So one can even wonder, why are we considering all the time complex space, very complex algebras? So why do we need the I? And then we start to go a little bit into philosophy, and we can say, like, even in Schrödinger equation, the I show up. So it's in there from the very beginning. It show up in the canonical commutational relations. So somehow I need the I. But at the same direction, we avoid, for example, I times identity is not an observable. So somehow it is in there because of physical information. So it has some physics in the I, yeah, in the imaginary unity. But somehow we also don't like it, or we say that basically we cannot observe these imaginary numbers. So at the same direction, or at the same point that we accept them, we don't want to have them around. Okay? So this theorem is, let's say, the easy version of Tomita Takesaki. Yeah? So that's the Tomita Takesaki only for standard subspace. And in these whole lectures, that's the only result that basically you have a much stronger version for phenomenal algebras. All the other results I'm going to talk, and almost everything I know about Tomita Takesaki modular theory for phenomenal algebras and standard subspace, it's basically the same, apart from the version for algebras, which I'm not going to show you. So if the Tomita operator is bounded, then it's easy. But if not, I will have some kind of much stronger theorem, Tomita. Theorem for Neumann algebras. And what this theorem says is the following. If you take your von Neumann algebra and you conjugate the von Neumann algebra with your modular operator, so it gives you another operator. Yeah. So notice that I need these deltas, for example, to preserve self-adjointness and things of that. So this thing here is precise your von Neumann algebra again. Maybe you are not getting too surprised, but it should be very surprising. Namely, the delta is not in your von Neumann algebra. It's an operator defined in the Hilbert space. So it's in so this thing here is in the whole B of H. Yeah, so it belongs to B of H, but not necessarily in the von Neumann algebra. But what I'm saying is, like, even though this operator may lie outside the von Neumann algebra, it preserves, so this unitary conjugation, so conjugation that is unitary, is preserve the von Neumann algebra. And if you take the J acting to your von Neumann algebra, it gives you the commutant of the von Neumann algebra. By the way, those things, these primes are for the symplectic complement, and the ones for the commutant are not for, or just by chance, or just because I like to use primes for very, very many different things to maximize confusion. If you look what is H prime in the case of the von Neumann algebra, it's nothing but the commutant here, prime in omega. So when you are talking about von Neumann algebras, taking the standard subspace associated to the commutant gives you precisely the symplectic complement of the standard subspace. Okay, so the prime is not just it's because it's related to the commutant prime. Yeah, it's a different one, but very closely related. Okay, but here we learned something very strong. Yeah, so that's the modular group. It gives you an automorphism of your von Neumann algebra. So it's a one parameter, or it's a one parameter family of automorphisms of your von Neumann algebra. And J gives you the commutant. And why is that important is because you kind of automatically get some type of dynamics in your von Neumann algebra. Yeah, so this T I'm calling T not by chance as well, even though it's just for now a parameter, but that's uh, just a second. Uh, uh, Give me just a second, I just need to. Uh, Sorry. Uh, So your modular operator, this one parameter family gives you some kind of dynamics. Yeah, so you can look to operators evolving with this parameter t, which could or could not be time. Um, and that gives some type of, therefore, of dynamics. And on the other hand, the J is very strongly related to locality. As you see, like that's you kind of get uh, a anti-unitary way of relating the von Neumann algebra with the commutant of the von Neumann algebra. Yeah, so that's quite powerful. Yeah, so that's probably the most powerful result in the whole theory. Okay, so I will not prove this theorem. The proof is quite complicated, so it would definitely take too long. If you are interested, I think that's the most legible proof can be in this book by Brattelin Robinson, which is mentioned in the bibliography that I suggested. So it's proved in full detail in there. You will see that's definitely not an easy one, but very powerful. Okay, so I would just to make some comments about what happens to like this one parameter group in terms of like kind of information or analytic information we can get about the of the modular group. So modular group. Yeah. So this delta IT is called the modular group. Yeah. We have the modular operator. So the modular operator defines this one parameter group, which is called the modular group. And I want to analyze something that's called the KMS condition. The KMS condition. Okay, so let's look to this, let's say, naive function in which I get two elements of my standard subspace, delta IT H with H2, and I want that H1 is in H and H2, yeah, also in H, but I want something else. I want it to be in the intersection with the domain of a full delta operator. Yeah, so I can calculate H2 into delta. And I know that there are many vectors for which this is true, yeah, even though delta is unbounded. Okay, so what we learned is, so because of these assumptions, f of t, or f, is a continuous function in the strip. So I will call, so maybe I should call it maybe a S. Well, looks like a dollar symbol, but it's a S with a extra bar just for differentiating from the Tomita operator. And I want to look to the strip of height 1/2. So what is that? So it's all the complex numbers such that the imaginary part is in between this number and 0. oh, sorry. Then F has a continuous extension. F has a continuous extension to the string. Okay, just because I can calculate the delta, the H2 is in the domain of a full delta, which means I can go with this power not only to real numbers but also to complex ones, just going to the to the boundary, yes, going to the imaginary part. And if it's in the domain of delta, it's in the domain of delta to the power t for any t less than 1. Okay, but not only this is true, but also, which is analytic, in the interior of the strip, S minus 1. Why? Well, basically because of the spectral theorem and Moreira's theorem. So if you integrate this function f of z dz into a closed curve, well, then I can just say, oh, this is integral of gamma of f of z, but remember f of z is just h1, and then I can write my delta as lambda it, and then the spectral projection with respect to lambda. Yes, so it's a full delta, yes. H2. And then I have, oh, sorry. So here, see, this is a D, I'm sorry, H2, and then you have a DZ, yeah. And then I use the continuity of the inner product to push the integrals, both integrals out, gamma integral, and the integral goes from 0 to infinity because delta is positive, so it's the integral is in the spectrum of, and then here we'll just put the lambda out, and I will call this, because this is a spectral measure, but if you really look to the measure that these two vectors define, so that would be d h1, h2, delta h. So just to say that the measure h1, h2, delta h is just by definition this in the measure given by this thing here. Say delta, of course, into the set h2. Yeah, so it's the measure defined by the spectral measure and the two vectors. The z, which is just to mention, it's a complex valued measure because the inner product is complex. Okay, so I have two integrals, the one with this complex valued measure, the one with my complex number, and I will, well, basically use Fubini's theorem to exchange those two. So it's the integral from 0 to infinity of the integral in the curve gamma lambda it dz dE delta h h1 h2. Well, but this function here is analytic, which means if you integrate into a closed curve, it gives you 0. So this is 0. Then we are safe. Yeah, so it's if you integrate my function f of z into a closed curve, it gives you 0. Therefore, Moreira's theorem guarantees that this function is analytic in the interior of the strip. Yeah, in the boundary, the analyticity doesn't make much sense. So here's just to recall definition. Okay, then I learned that I have a continuous function in the strip, closed one. In the interior, it's analytic. And I also learned something about what is f of t minus I And what is f of t minus I? So that should be h1. And then I have a delta it and a delta. Let me write the whole thing. So it's my z will be t minus I, h2, which means I have a full delta that I can, in particular, even split. Yeah? So that will be delta 1 half h, delta it, delta 1 half everything with h, h2. Delta is positive, so I can pass it to the other side, not paying any price. That's just h1. Then you have it, h, delta h, 1 half h2. But now you can also use the fact that j is equal to 1. So I can just insert a jh in here. But I have to pay a price when I pass one of the j's to the other side, namely conjugating the whole thing. So that would be jh delta h 1 half h2. So I'm conjugating by reversing the order of the inner product. And then jh, yes. No, I lost some. Ju- The delta it. Delta it, delta h 1 half h2, and then jh delta h 1 half h1. Now I remember that jh commutes with delta it, so this is just delta 1 half, or jh delta 1 half, but then this is s, and h2 is invariant with respect um, to s. Therefore, this is just delta it h in h2. And the same thing here, yeah, so this is just sh, but h1 is invariant, so it's a fixed point, which is this thing. I can also write as f of t bar. Okay, so I learned a lot about this, like this modular group, namely, if I get vectors in my standard subspace, I have a function which is, so if I get vectors of this type, I get a function which is analytic in the strip, in the interior of the strip, closed in the continuous in the closed strip, and when I go to the other boundaries of the strip, so in the zero I have, of course, the function as it is, but when I go to -1, I get the conjugate. Here, just I get a message that my connection is unstable. Did you get what I said, or was it cut out? Okay, so just checking, are you hearing me well? Yeah, okay. Yeah, so you have this boundary condition that when you go to the imaginary part equals -1, you get the conjugate function. Yeah, so it's an analytic function that's in, okay, the real boundary, it is what it is, but in the imaginary part equals -1, the boundary value is equal to the conjugate of the one in the upper boundary. And so you can ask like, okay, well, why is that relevant? Or like, what do you really learn with that? And I will tell you what you learn. And probably by the end of what I'm going to tell you, you'll say, okay, I still don't understand. But then after the second thing I will tell you, you will realize how important it is. So let's look to one particular case of that situation, which is when I take my vector h1 to be of the form A in the vacuum. Then I have my delta ith acting into another vector of the form B into the vacuum, so A and B in the algebra self-adjoint. Yeah, so here I'm also looking to phenomenon algebra, so let me use M. Yeah. So the advantage of the von Neumann algebra is because of the commutant. Yeah. So if you take another type of algebra, for example, a C star, when you take the commutant, you end up with a von Neumann algebra. And then when you take the bicommutant, if it's a von Neumann algebra, is equal to the algebra itself. Otherwise, it's something which is bigger than the given C star algebra. So that's why it's useful to have the von Neumann algebras, because when you go to the commutant, it's better behaved. Yeah, so that's the reason we are shifting to von Neumann algebras. But okay, so I have two self-adjoint operators acting into my vacuum, which means in particular that this thing here is in my standard subspace and this thing here is in my standard subspace. So remember that the vacuum should also be invariant by the modular group. And the reason is just because if you look what is delta H or what is SH into the vacuum, yeah, so it's SH into the vacuum, which is just SH into identity acting into the vacuum, it should be equal to the identity star acting into the vacuum, which is just the vacuum. So the vacuum is invariant by S, which means it's invariant by delta Nj. Okay, so the vacuum is invariant by delta, so it's an eigenvalue it's an eigenvector with eigenvalue 1, which means I can apply my modular operator and keep it invariant. So I just for free added one modular operator in here. Okay, now thanks to Tomita theorem, this is also back into M and it's also self-adjoint. Yeah, so that's why I inserted this delta minus IT and just not the same. So I put it in there exactly so I lay again into my von Neumann algebra. But the condition we just said is that F in T minus I should therefore be equal to delta H IT B delta minus IT H omega with a omega. Yeah, so just the conjugate. Okay, but what is this function? Well, this is my state omega calculated in the vectors A, and allow me to call this sigma t of B, while this one is just omega sigma t of B A. Yeah, so that's the omega is the vector state associated to the vacuum. Yeah, so the vacuum is the vector is represented with omega, and the state is represented with the small letter omega. So what's happening here is, since A and B are self-adjoint, so I don't care about stars, that they are flipping inside the state. So A and B do not commute, A and sigma t of B do not commute, but inside the state omega, they don't commute, but the analytic extension from the real boundary to the imaginary boundary, yeah, so the imaginary particles minus one, precisely make the operators to commute inside my state. And here by sigma t, I think it was clear, of B is equal to delta ITH B delta minus ITH. Yeah, so that looks quite interesting. Yeah, so that's in particular if you take t equals 0, so the extension from from the point 0 to the point minus I precisely give you the commutation between A and B inside omega, just as an analytic extension. Yeah, so you basically get commutation inside omega by analytic extending. Okay, so that is the first reason, which is mathematically interesting, but you say, yeah, but I have absolutely no idea why this is physically relevant. But I will show you maybe the physical intuition. So this is called the KMS condition. but that I will write into a second. But let me physical intuition for the KMS condition. So let me try to be kind of cryptic and start with some state, some density matrix, which is e to minus beta h. And here maybe I should use another h because it's
Yeah.
so I cannot use the curly one. I cannot use the straight one. What should be my h? I don't know. It cannot be small h's in the standard subspace. I am lacking letters. Okay, I will use h, but this one is the Hamiltonian. Divided by the trace of h minus beta h. Yeah, so I'm supposing h minus beta h is trace class, and I'm considering this density matrix, and I'm considering the state omega, which in an observable A just give me the trace of rho times A. Yeah, so reasonable, I hope. And you all should, I guess, be questioning why h minus beta h, or maybe you are just so familiar with the concept that you just like assume that was very natural to choose this dense matrix because this is, well, the Gibbs distribution. Yeah, so that's the dense matrix that talks about thermal equilibrium conditions. Yeah, so it's h minus beta energy is taking those probabilities is precisely the choice that gives you thermal equilibrium state. Okay, so fine. And how does the time evolution of an operator A is defined? Well, that's also e to I h t a e to minus I h t.
Oi, licença.
Just a second. I'm sorry, somebody came to check the smokers, and so okay, so I just had to tell that I was like lecturing because it's not obvious because I'm just talking to the computer. Okay, so yeah, so the time evolution of the operator A is given by this formula. Yeah, so just using what the Hamiltonian evolution. So let's see what happens if I look to f of t, exactly the same one, which would be the omega of A alpha t of B. Well, this is by definition just, well, the trace of E to minus beta h. Allow me to just call this the trace of the E to minus beta h z, yeah, so the partition function. A, and then by definition, it's TH B e to minus ITH. Okay, so just replace things by their definition. But now you kind of see what's going to happen, right? So what happens when I go for T minus I, when I go to the other boundary? Well, if I'm supposing that my function e to minus ht has a well-defined trace, and it's, well, in particular, it is well-defined, I will have that this extension is just given by a, and then I have e to, oh, sorry, it's not I, it's minus I beta. So when I put an extra, so when I take t equals to minus I beta, I get, sorry, plus I beta. So I get I with I get a minus, and then I have here minus beta h, but I also have the term with the t. then I have B, then here I have an extra sign, so it's a plus. So, okay, let me go with the complex part first. So it's minus IHT, and then I have the part that comes from the imaginary part, which is plus beta H, and that's the whole thing. But thanks to the cyclic property of the trace, I can pass this operator to the other side, meaning this guy cancels out with this one. And if I also use the cyclic property to pass A to the end of this trace, what I'm getting is the trace of E to minus, or sorry, to, yeah, so minus beta H over Z. So this thing here is this operator. Then I have E to minus IHT B, sorry, it's a plus, E to minus IHT. And finally, the A that I sent back to the end, which I can recognize as being the trace of H minus beta H Z. And then here I have the alpha T of B again, A, which is again equals to the omega of alpha T, B, A. Aha. Okay, and now I hope you got a little bit more interested into these relations. So Gibbs equilibrium condition precisely satisfies the relation I just checked for the modular operator for beta equals minus 1 and for the dynamics defined by the modular operator. Just to tell you some part of the story, so the KMS condition showed up in a very different context from the modular theory. Yeah, so the first time it was derived, it was by Kubo Marti Schwinger, yeah, that's sorry, by Hag Hugenholtz Winiken in the sense of thermal equilibrium states. Yeah, so that's the name KMS comes from Kubo Marti Schwinger, which well, obtained first this relation, but in the context of showing that the thermal equilibrium state should be characterized by the KMS condition, was a work by Hag, Hugenholtz, and Winiken. So what they do in this work is basically saying the following. So density matrix are not a very general concept because you require this E to minus beta H to be trace class. Yeah, so that's if the operator is trace class, it's in particular compact. So that's definitely not a good concept to have because if E to minus beta H is compact, it has discrete spectrum. So it definitely don't deal with Hamiltonians which have continuous spectrum. So I need something more general for doing that. But in physics, when you want to characterize thermal equilibrium condition, usually you are taking some thermodynamical limit, which involves you putting your system into some kind of box, which typically also forces the Hamiltonian or any other type of observable that you are looking to become discrete spectrum. And later you take the continuous limit, yeah, so the thermodynamical limit. So the idea of Hugenholtz and Winiken was exactly to look what happens in the thermodynamical limit. So to characterize the thermodynamical equilibrium by this condition that survives the thermodynamical limit. And this condition is the KMS condition. So one says that a system satisfies the KMS condition for inverse temperature beta precisely when this function here has a continuous extension to the closed strip with height beta in the imaginary plane, which is continuous in the closure, analytic into the inner part of the strip, bounded, and in the boundary it satisfies these two conditions. Yeah? So that's for in the real boundary, the function is given by this formula, and in the other boundary, so the boundary with imaginary part beta, it gives you the flipped inside. So that's what characterizes thermodynamic equilibrium. That's the most general characterization in phenomenal algebras, in operator algebras. There are other versions of KMS conditions, even into similar contexts, some of them even copied from the KMS condition. But in C-star algebras, in phenomenal algebras, apart from some details about the system, yeah, so the dynamical system having to be continuous or weakly continuous, so it depends a little on the type. That's the most general definition of thermal equilibrium, which survives the thermodynamical limit. And that's a tricky thing that I avoided discussing too much. So the point is that remember that here when I was talking about this condition of the function being analytic, I start saying that my H2 is in the domain of delta H because I wish to write the extension of the operator. Yeah, so I want to go calculate the operator into delta. Yeah, so delta of the vector. But one thing that one can prove is that if you keep the inner product, just look to the function and not to the operator, this restriction can be dropped. So it can be done for any vector into H, and you don't need the restriction that H2 has to be in the domain of a full delta, but you can never write, of course, this thing here. Yeah? So if it's this is the case only if H2 is in the domain of delta, but if you never write such a vector and you only consider the function given by the inner product, then it holds in generality, which means the KMS condition only needs to be checked into a dense set. Yeah, and that has to be with the modulus maximus principles for analytic functions. Yeah, so it's some of these magics that happens for having analytic functions. Okay, so the operator do not have an analytic extension, but the expected value does, or the matrix coefficients does. Okay, so what I learned is even more, and maybe even more physical now, is that my modular group, which I define it this way, so if I have the state omega, it is, okay, so conclusion, omega is a sigma t minus 1 KMS state. And here, what I mean by this thing here is my beta, and this one is my dynamics. Dynamics. And beta is usually 1 over kBt. So don't ask me why it's minus 1 and not a positive 1. Okay, you may ask. It usually has to do with some mismatch between notation physicists and mathematicians. Yeah, so it's and the condition satisfies this condition with inverse temperature minus 1, which is physically a little strange. But I could easily just reverse the dynamics. Yeah, so the sigma t is the modular dynamics, not only the dynamics, but the modular one. Yeah, so that's sigma t of A is equal to delta IT H A delta minus IT H. Yeah, so if I have defined it, let's say if I define it, let's say alpha of T of A equals to delta minus ITHA delta ITH, which is just reversing the signs, then it will be a KMS state with inverse temperature 1. So if you are too bothered by the fact that my coefficient is minus 1, it's just because of some problem with like what is the dynamics is defined kind of with minus the Hamiltonian instead of the Hamiltonian. Okay, so notice that it's very magical. I start with a dynamics, oh, sorry, I start with a state and I magically end up with a dynamics that make my state a thermal equilibrium state for some dynamics. That's also historically interesting and relevant I'm sorry. So the situation before in matrix mechanics or in quantum mechanics was usually the opposite. You have very many dynamics, but you could not find any um, state which is a KMS state apart from the easy situation when you have a Gibbs condition. Here we have the opposite. So we have a state and we immediately find the dynamics for which my state is a thermal equilibrium state. And the question is this dynamic physical? Yeah, so that there is now, I have two sides of the same problem. So finding equilibrium states for dynamics. And I find now this other point of view, which is like I have my state, which is a thermal equilibrium state for a dynamics that I defined abstractly by the modular group. And okay, so these dynamics can or cannot be physical, or because okay, so kind of like what you show is every cyclic and separating state is a thermal equilibrium state for some dynamics. Yeah, so that's the question is which dynamics. That's the reason why you often hear the name modular Hamiltonian. So what's modular Hamiltonian? So the Hamiltonian or the modular Hamiltonian, which again denote H, even though it's not the standard subspace, it's usually defined as minus the log of delta. So it's either this one or minus 1 over beta log of delta, depending if you wish to talk about thermal equilibrium for temperature, inverse temperature beta or not. So if you don't put the temperature, so it's minus log delta. Yeah, so again, the minus is because if you define the Hamiltonian with the flux, so the time evolution with this Hamiltonian, you get the correct, that's the KMS with temperature 1. Yeah, so that's it's just to correcting the mismatch between physicists and mathematicians' direction of evolution of time or the sign of the Hamiltonian. One interesting thing that I need to make you aware is that this Hamiltonian not necessarily or in general it does not belong to your phenomenon algebra. Okay, so be careful. This is not necessarily a physical Hamiltonian in that sense, because remember that the modular operator usually don't lives into your phenomenon algebra, so that's quite the opposite. So it's an operator that's not only defined in the phenomenon algebra, but it's to the whole Hilbert space. And therefore, this Hamiltonian is not in your phenomenon algebra. So this is self-adjoint, yeah, but it's so the point is it lives into, so let's see where it lives. So it lives into B of H self-adjoint, but not in your phenomenon algebra. And the reason is because usually this operator has some part that evolves into the commutant of the phenomenon algebra. So what we see is that kind of this modular Hamiltonian or the modular operator, it behaves very similarly into the algebra and into the commutant. Therefore, it's not possible that this modular Hamiltonian lives into the phenomenon algebra. Otherwise, it will give you a trivial flow into the commutant, and it cannot be true. So kind of H has some component that comes from the algebra and some component that comes from the commutant. So in some cases, so in some special cases, um, we can identify what are those parts, and those are some part which is a, let's say, a physical Hamiltonian minus JH physical J. Yeah, so it's you have a part that lives into the phenomenon algebra, but then you see here, so this is a part that lives into the phenomenon algebra, and that's a part that lives into the commutant of the phenomenon algebra in such a way that it gives the correct evolution on the phenomenon algebra and on the prime. But again, it's a special situation. I think it's only type 1 and 2 phenomenon algebras. It's not true for type 3, for example. Okay, so another point that maybe definitely density matrix are not a general feature. That's what's many areas like density matrix are kind of use it as some general concept, but it's quite the opposite. So under some my requirements about your local net, your phenomenon algebras have always to be type 3, which means no trace around, not even a semi-finite one. So things are a little bit more complicated than one can anticipate. So let me just make like one physical comment and then show you that the standard subspace of a phenomenon algebra is separating. And this physical comment that I want to do, it's not very detailed. I'll just give you some intuition of why those things are important. So it's uh, I think it's Jenny often asks me, okay, but what's the physical meaning of that? And that's a very relevant question. So if you're a physicist and you're doing math physics, you should always be asking this question. So you should never lose track of what are the physical intuition behind concepts. Not always you have a very clear picture, but every time you can, you should. And now I will maybe elaborate a little bit more, even though not giving too much detail of why this standard subspace um, uh, ideas and this real structure can be relevant. So again, everything is in between the real and the complex structure of a Hilbert space. Okay? Point is somehow the modular group gives you what is your natural candidate to the modular group. Yeah, so the dynamics should be kind of related to the modular group. Otherwise, you are kind of in trouble. Yeah, so because you want your, for example, your vacuum to be your equilibrium state, and the only dynamics or the only modular group that provides that is the modular group. Yeah, apart from the fact that you can cut it only to the algebra and forget about the commutant, that's the unique one. Yeah. Um, okay, then what happens if you um, try to just look to the internal structure of things? And for that, again, I'm not going too much detail, but I can try to see what is a standard subspace from its internal point of view. So I start with a standard subspace. And here by a standard subspace, since I'm not looking to that contained into H, so I'm forgetting this part, I am thinking of it as a real Hilbert space with a one parameter I will call unitary, but since it's a real Hilbert space, maybe I should call it orthogonal. But okay, so allow me to abuse notation because I like the complex structure. So it's a one parameter unitary group if you prefer a orthogonal one. So this is a real Hilbert space. And this is a one parameter unitary orthogonal group. Okay, so why is that relevant? Because that's exactly the situation I have with modular theory, right? So I have here H is a closed real subspace of a Hilbert space. Therefore, it is a Hilbert space itself with the same topology, I mean, with the same norm. Just because here I can just take the norm or the inner product given by the real part of the complex inner product. Yeah, so that's so this is the type of duality I'm having. So here I have a complex Hilbert space with an inner product, and I have here a real Hilbert space with a real inner product, and the real inner product is just given by the real part of the complex inner product. The interesting fact is that the topology is the same. So it induces the same norm because the norm is already real. So when you take the real part of x, the inner product, the real part of the inner product between x and x, it's the same thing as the inner product between x and x. So the topology is the same, the norms are the same. So the inner product is not. So the concept of conjugation and whatsoever, it's not the same. And my question is, can I make this construction or a construction of just start with a real Hilbert space and a one parameter unitary group, construct a bigger space, a complex one, so namely a complexification, in such a way that my one parameter unitary group is my modular group? And the answer is yes. And that's what I will call, just as a nickname, the internal structure of a Hilbert space. So I'm not going to go into too much detail, um, but it has to do with like the fact that you have to tell what is the imaginary part of your inner product. And the point is like if you just start with this, so with a real Hilbert space, which has its own inner product. So allow me to, because here I'm inducing from, yeah, I'm getting the inner product from here. And when I'm looking now, I have just a real Hilbert space, which has just a real inner product with this one parameter group. And what we can do is basically first look to the complexification, yeah, so that which looks like H plus IH. But then I can induce in here a different inner product. And the inner product is given by a specific formula that has to do with what's called the polarizer. Yeah, so allow me to just give you a very vague idea because I still wanted to talk about this physical, small physical application of the whole thing. So if you look to the imaginary part of the inner product, so maybe I just write it this way. So the imaginary part of x and y is smaller or equal, well, than the modulus of the full inner product, so no surprising here, which by Cauchy-Schwarz is less or equal than the x norm of y. Say, okay, what have I learned with this information? Is that if I look to my Hilbert space, not as a complex Hilbert space, but just as a real one, yeah, so it's the same set with the same structure, apart from the fact that I forget about complex linearity. So I don't identify Ix with like I times X because I don't have it. So it's a different vectors. Yeah. So for really, if I speak in terms of real linear, so these two vectors are linearly independent. Yeah. So it's a new vector space. If it's finite dimensional, it has double the dimension. If not, well, it has kind of double the dimension in another sense. Okay, and in this space, I can just put, as I mentioned, the real part of the inner product of the original one as my new imaginary part, so my new inner product, uh, which defines the same topology. Yeah, so the norm is the same. If the norm is the same, this thing here is a bounded sesquilinear form. Yeah, so because this thing here is the norm that's induced by the real part of the inner product, which is again a little surprising, but again true and simple, which means that the imaginary part of x and y can be reconstructed from the real part. So it should be the real part of x, and then I have some operator dy. Yeah, so that's what you get by, well, it goes with several names. It can be a consequence of Riesz representation theorem. Some people will call Black-Milgren. So different names, but a bounded bilinear, because here it's sorry, it's a, yeah, so in terms of a real Hilbert space, it's bilinear form will just be given by, well, an operator, a bounded one, acting to the real part. And the interesting fact is that this D can be determined in terms of modular data. Yeah, so that's D is just, let's see if I remember, I think it's I delta minus 1 divided by delta plus 1. I would have to check if that or it's minus that, but it's something of that sort. Which means I can use my modular data to reobtain the imaginary part from the real part. Yeah, so that's should not be a surprise, and since delta comes from this interplay between real and complex structures. So it's not a surprise that you can reobtain the imaginary part, which means that I can, in this new Hilbert space, not using the usual inner product, but I can in this one define the inner product, which is given, of course, by the real part plus the imaginary part. So let's go in parts. So first things first, I can, let me have problem with closing, yeah. So first thing is like I can extend U to H plus IH unitarily. And for this extension, I can look to the generator. So it's this U is equal to some E to IH T, yeah, so U of T. And I can play with this generator to construct my modular operator. Yeah, so it's so after realizing that, I can basically say, well, my inner product X and Y will just be given by the real given one. So the real part will just be the same. And the imaginary part will just be again given by the real one. And then I will put in here the polarizer. Yeah, but the polarizer I will kind of force to get the generator of the complexification. So that would be I times the generator, how I call the generator, H. Okay, I have to start stopping using H to too many things. So let me use K or A for the generator. AT. Then I can put just A minus 1, A plus 1, Y. And now this gives me a new inner product, a complex one, and I can take the closure or the completion of H plus H with this inner product. Yeah, here completion. So with this construction, you start with a real Hilbert space with a one parameter group, and then you find a complexification in such a way that the one parameter group is the modular group. And again, why is that interesting is because the modular group has a clear interpretation as the dynamics for which your initial state, yeah, so the state you start with, is a thermal equilibrium state. Okay, so one thing that one can do is, for example, start with, so a small application, or like, let's call it Klein-Gordon standard subspace. So one can just say, I'm looking to square integrable functions, but not all of them, only the real ones of the real line. Yeah, so it's, well, maybe I just should write. Now I can having problem here. Yeah, okay, to erase it from R into R. Yeah, so could be much dimensional, so that's not the important part. Yeah, so I could put a D in here. But the important information is like I'm just taking real valued functions. And remember that oftentimes these real valued functions or real valued solutions have some interpretation. And in some sense, I want my dynamics to be given by, and here, sorry about the use of delta. Maybe I should use nabla square to avoid confusion um, with the modular operator. But then I want those things to be solutions of the Gordon equation, which means somehow I want to look to my dynamics or to the space related with these modular operators. So this thing here is uh, a generator, yeah, it's a positive operator. Remember that minus the Laplacian is positive, which means I can try to construct some um, some complexification. So maybe I shouldn't call it like it should maybe be. It's always a problem of calling things by different names. Uh, I don't have a better name than H, but then I will have problems with the standard subspace. But okay, so if I want that to be true, I can try to then construct some modular group, which is just given by this one parameter group defined this way. Yeah, so it's I can just look to U of t to be precisely E to I H t. So it's a positive operator, which I can therefore define the unitary evolution. And what I really want to have is that this one parameter unitary or orthogonal group acting into this standard subspace that I will not call H, I will call K just for avoiding the H that I used in the other side, is the correct evolution. Yeah, so and that's the comment that I just gave to you is the way of doing that. Yeah, so basically what you have is like you have some given uh, dynamics into some real Hilbert space, and then you want to complexify into a smart way such that you can construct your Hilbert space having the uh, unitary original group given into the real subspace or the real space as your evolution or as your modular evolution. And the reason for that is because if you want to, again, I'm just repeating myself. So if you want to have your state to be your thermal equilibrium state or to satisfy KMS condition for this one parameter group, it's better that this operator, this unitary group, have to be related with your modular Hamiltonian. Yeah, so that's the physical reason behind it. Some concepts which are very strongly related, and you can check into that to see a little bit more of connected ideas, is to look to these one particle structures. Now you can see that, for example, in the papers of Bernard Kay, which I think was the one introducing the concept. So it's not always exactly the same, but you see exactly the same kind of idea of starting with a real space and complexifying this one particle real structure to some complexification. So last thing into this final 10 minutes, let me just show as I mentioned, that the standard subspace for a von Neumann algebra or for even a unital star algebra, subalgebra of P of H is cyclic, yeah, because I have like get like a problem last time. I was confused what to do. But here, so if A I star, it's a unital star subalgebra of B of H and one okay, yeah, so that's yeah, so this is the assumption, yeah. So if A is a unital is a unit of measure, then omega is cyclic for A if and only if omega is separating for the commutant. And well, for that I would need like a small lemma. So which is the following. So if you take let P in B of H be the projection or the orthogonal projection onto, and then I take my algebra acting into my vector and then the closure, then P belongs to A prime. Yeah, so that's basically if you look to all vectors which are obtained by acting into your vacuum with your algebra, and you take the projection, the orthogonal projection into the closure, yeah, so it's a closed subspace of H, therefore there is a bounded orthonormal projection related to it. And if I look to this projection, it lies into the commutant of the given algebra. The proof is not too complicated. So the question is, what happens if I look to A, P acting into a vector X? And remember that X can be decomposed in two parts. So one part that lives in here and then one part that lives into the orthogonal. So allow me to already like jump one step and say the part that lives into this subspace is the limit when n goes to infinity of some sequence of operators acting into omega plus some part which lives into the orthogonal. Yeah, so it's a omega orthogonal. Okay, so since P is bounded, it commutes with the limit. In Y, it gives you 0. So this thing here is just a P of the limit when n goes to infinity of a n omega. And then P is bounded, therefore it commutes with the limit. So it's the same thing as, oh, sorry, so this goes out. So this is the same thing as the limit when n goes to infinity of n omega, which I can just again identify as n goes to infinity of p of n omega plus a of y. And here I have some claim that this thing here belongs also to a omega orthogonal. So this term in here is just 0. Yeah, so that's my claim. I will show it in a second, which is of course just p of the limit and then it goes to infinity, and then I can put my a out, and then the omega n yes, plus y, which is just pa of x, of x. So what I did is exactly I start with AP, ended up with PA, just by saying, oh, okay, take the orthogonal decomposition, and then the part which has orthogonal is 0, you have the limit, the multiplication with a fixed operator on the left is continuous, so I can pass it to the inside. A times AN is back into my von Neumann algebra. Therefore, if I project this thing again, it's trivial in here, and in the orthogonal it should be 0. So my claim is that this is in the orthogonal, and therefore they should commute. And why what I'm saying it's true? It's because if you look to A, so if you look to anything of the form B omega, inner product with A omega, A y, it's the same thing as A star B in omega with y, but A star B belong to my phenomenon algebra. Therefore, A star B in omega belongs to A omega, but Y belongs to the orthogonal of A omega, so this is 0 for all B in the phenomenon algebra. And that's exactly the definition of B, this being in the orthogonal. Yeah, so that is true. So this operator projection commutes with everything in A or all A in the phenomenon algebra. Okay, and now the proof of the proposition. Yeah, so it's if omega is separating for A prime, what I have is that that 1 is equal to the projection into the space that I just told you, because what happens if you look to the identity minus the projection into A omega bar into the vector omega? So this thing here belongs to my commutant. This thing here, I just proved you that it belongs to my commutant. Therefore, the whole thing belongs to the commutant. But this is just omega. And notice that omega is of the form 1 times omega, and 1 is in my phenomenon algebra because I'm supposing the algebra is unit, not the phenomenon algebra, in the star subalgebra, which I'm supposing is unital. So this is just omega minus omega, which is 0. But then since omega is separating, that implies what I just told you. But if the orthogonal projection into this closure is 1, it's because the space is dense. Or is the whole Hilbert space. On the other hand, so if you start with omega, if omega is cyclic for A, then you can look to A prime into omega and say that is 0. And I want to conclude that A prime, oh, sorry, A prime in omega is 0. But that implies that A times A prime in omega is 0. Here I'm supposing A prime lives into the commutant, A lives into the phenomenon algebra. But since they commute, I learned that A prime into A omega is 0. But this set here covers all the A of omega, which is dense. So it implies that A prime vanishes on a dense set, and therefore it's 0. Yeah, because it's bounded. Okay, so why have I proven that? Just because that was the missing point that I forgot yesterday. Proposition H equals to A omega bar is separating. Namely, H intersected with IH is just the null vector. So how does the proof go? So if X belongs to H inter IH, it implies that X is equal to the limit, self-adjoint, of AN omega with AN self-adjoint, but it's also the limit of I BN omega with BN also self-adjoint. Okay, then what happens if I look to some operator in the commutant acting to omega times this vector x? Well, on one hand, it should be A prime omega with, so it's the limit, with a n x, which is just equal to the limit, and then it goes to infinity. And then I can pass the a n to the other side. So it will be a n a prime omega with x, but a n and a n prime commute. So I can just shift then. But then this thing here goes to h. So that's a prime into, oh, sorry, x omega. Omega. On the other hand, I can play the same thing with the I and say that it's a prime omega with I bn omega. But now, okay, the bn is self-adjoint, so I can pass it to the other side with a plus, but the I gets a minus sign. So therefore, it's the limit when n goes to infinity of minus I bn a prime omega x, or omega. And then I can pass this thing here to the inside exactly for the same reason, yeah, because bn commutes. But then what I get is minus a prime x omega. So the end of the story is that this thing here is equal to minus itself. Yeah? So just look into this thing here. So the only number which is equal to minus itself is 0. So this thing here is 0 for all a prime in omega. But remember that a prime in omega is a dense set because I'm supposing that omega is separating, which means it's cyclic for the commutant by the proposition, and that implies that x has to be 0 because it's in the orthogonal of a dense set. Okay, so that's so it was a little bit trickier than I recalled. So you have to really go through this relation with the commutant to get. So it is a play between being of the form a limit of I an and an and I bn, but also you have to play with the commutant to be able to pass things through. Okay, with 3 minutes delay, I again asked for forgiveness to Bruno for holding his lecture for 3 minutes. And you are, of course, all welcome to send me questions by email or asking tomorrow in the beginning of the lecture. Thank you very much.
Shall we stop the recording like we did yesterday and then restart?